Similarity. Well, congruence and similarity have, pun intended, similarities. Rigid transformations. We have translation, that's sliding one thing from left to right or up or down or diagonally. We have reflection, flip it across a line, so like across the line of symmetry. And we can rotate about a point. What do rigid transformations preserve? Well, they preserve angles and distance. In other words, rigid transformations make the objects still congruent. Now, who preserves angles but not distance? Well, that would be similarity, non-rigid transformations, which would be a dilation. Okay, so translation, we slide, rotate, we rotate about a point. Reflecting, we flip across a line. Dilation changes the distance between points on an object. So we usually have a center of dilation, and then it stretches out from there. Okay. Now we've got some other terms. Scale factor. The scale factor is the constant number which multiplies the side lengths of the original shape to create the dilated shape. So as we take a look at this object, triangle ABC is similar to triangle WTF. If I take 24 times half, I get 12. 26 times half, I get 13. 10 times half, I get 5. So the scale factor is 1/2 from triangle ABC to triangle WTF. If I wanted to reverse it, the scale factor from WTF, that triangle, to triangle ABC would be 2. Corresponding parts of a shape are the parts that match based on the position relative to the entire shape. So we can look at these two quadrilaterals, AT and ZL. Well, actually, yeah, ZL would be corresponding sides. Angle postulate for triangle similarity. If two triangles have two pairs of corresponding angles which are congruent, then the triangles are similar. Note this only works with triangles. So we take a look at the outer triangle. Triangle FNU is similar to triangle SXU because angle F and angle S are the same, and angle U is the same for both triangles. Side angle side postulate for triangle similarity. If two triangles have two corresponding sides proportional and the angles between them are congruent, then the triangles are similar. So as we take a look, we have triangle ABC. It has the sides 16 and 40, and triangle FGH, which has the sides 12 and 30, and we're told that angle C and angle H are congruent. If I take 40 times, let's see, times 3/4, I get 30. If I take 16 times 3/4, I get 12. So those two triangles are similar. Side, side, side postulate. If two triangles have three proportional pairs of corresponding sides, then the triangles are similar. So if I can take all the sides of triangle ACT times a scale factor, and I get triangle, I'm trying to think, ODG, then it works. So basically, if I take half of all the sides in triangle ACT, I get the measurements for ODG. Example 1, identify the transformation that occurred to transform rectangle ABCD to rectangle A prime, B prime, C prime, D prime. Well, it looks like we just slid, and we can even look at definition. It's a translation. We translated count from A to A. We translated right 8 units and up 4 units. Example 2. In the diagram, we have triangle ABC, and we want to know that it's isosceles. So how can I use some rigid transformations to prove that it is? Well, one of the first things we can do is to construct a perpendicular bisector of the side CB. In other words, cut this bottom side in half, and then reflect angle ABC across that perpendicular bisector. And if angle ABC matches up with angle ACB, that would also have the two sides corresponding, being congruent, then that would show that the triangle is isosceles. Example 3, explain why the angle-angle criterion for triangles proves similarity. Well, got to know that all three angles of a triangle add up to 180. So if we know two of the angles, we can find the third angle because we just take 180 minus the other two angles. So if two angles in one triangle are congruent to the corresponding angles in a second triangle, then the two triangles have to be similar because their corresponding third angle would also have to be the same. Excuse me. Example 4, in the figure, we want to know if the triangles are similar. And we've got some notation here. First off, both triangles share angle C, so they have that angle in common. We're also told with those arrows that line AE is parallel to DB. That means triangle ACE is a dilation of triangle BCD. Therefore, angle ACE is similar to triangle BCD. Excuse me. Example 5, which figures are similar? Well, this one takes a little bit. We got to do quite a bit of comparing. So start with compare triangle 1 and 2. Short side of 1 to the short side of 2. And then the long side of 1 to the long side of 2. So the short side of 1 is 6, the short side of 2 is 7. The long side of number 1 is 10, the long side of number 2 is 9. And we get 0.86 on the left. That doesn't equal 1.11 on the right, so 1 and 2 are not similar. Do 1 and 3. Again, same thing, so 6 to 3, 10 to 4. 2 does not equal 2.5 when we simplify those fractions, so 1 and 3 are not similar. Check 1 and 4. So 6 to 3.75, 10 to 5. 1.6 does not equal 2. When we divide those fractions, they're not equal, so 1 and 4 are not similar. So notice I just took 1 and compared it to rectangle 2, rectangle 3, and rectangle 4. Okay, so now I've compared 1 to everybody. Now I'm going to start with 2 compared to 3 compared to 4. So 2, 7 to 3, 9 to 4, 2.33 does not equal 2.25. 2 and 3 are not similar. Check 2 and 4. So 7 to 3.75, 9 to 5. 1.87 is not exactly equal to 1.8. So 2 and 4 are not similar. Now we've got one last one to check, 3 and 4. So 3 to 3.75, 4 to 5. Both of those, that's an error. 0.8 does equal 0.8. Therefore, 3 and 4 are similar, but you can ignore that not equal sign and put an equal sign because they are exactly equal. Example 6, are the figures similar? Well, we've got, looks like 2 of the sides, but I need one more piece of information. I don't have enough. I need to know if the third side is also proportional. I don't know that, or I need to know the angle in between is the same. Okay. Example 7. What piece of information do we need to prove that triangle NQR is similar to triangle PDQ? Well, first off, we have that NR is similar to PD because I take 7 times 2 to get 14. We also have those inner angles, NQR and PQD, are equal because they are vertical angles. I just need one more angle to be congruent. So either angle N has to be congruent to angle P or angle R has to be congruent to angle D. Now example 8, we're told that the two figures are proportional, that they're similar. The two triangles are similar. Triangle ACE, the big one, is similar to triangle BCD. So that means I've got quite a few proportions that are congruent. I can take the long side of the big triangle, AC, to that corresponding side of the short triangle, BC. That should be equal to another side of the big triangle, AE, and it's corresponding in BD. So all we're doing is comparing corresponding sides. And then we could do AC to AE would be should be equal to BC to BD. CD and CE to BD and AE, CD and BD, CE and AE. Example 9, create a figure that is similar to an equilateral triangle with perimeter 33 feet and explain why it is similar. Well, first off, an equilateral triangle means all the sides are the same. So 33 feet is the perimeter, so divide that by 3. So one side would be 11 feet. Now just take the 11 times any number I want. So multiply by any scale factor to either the perimeter or the side to get a similar triangle. But you would have to say that it is an equilateral triangle with a particular perimeter. So if I took everything times 2, all the sides would be 22. 33 times 2 is 66, so I could say an equilateral triangle where each side is 22 feet, or I could say an equilateral triangle where the perimeter is 66 feet. Example 10, a patio is designed by using 2 types of tiles. The tiles are similar isosceles triangles. The lengths of the sides of the larger triangle are 6 inches, 6 inches, and 4 inches. What would the dimensions of the smaller tile be? Well, start with, we just need to multiply by any scale factor to each of the sides to get a similar triangle. Since we want it to be smaller, we could take all the sides by a half. So 6 times a half is 3 inches, 6 times a half is 3 inches, 4 times a half is 2 inches. That would work. Example 11, we have square, rectangle, ABCD. It's dilated with a scale factor of 2 centered at 1, 1. What are the coordinates of the new figure? Well, what we do is we put the center of the dilation, and then we kind of count from that center to, let's go to C. Well, we'd have to go up 1 and left 1. And then that would be a scale factor of 1. Since I want a scale factor of 2, I followed that slope twice. So up 1, left 1 once, up 1, left 1 twice gets me to the point -1, 3. Now we do the same for the next point. And so let's do D. That means we're going to go down 3 and left 1, so that we follow that again, down 3 more and left 1. We get to the point of -1, -5. Now let's follow for A. And that looks like we go down 3 and left 5. Down 3 more and left 5 gets us to -9, -5. And then we do for A, or sorry, that was A. Now we do B. Looks like we go up 1 and left 5, go up 1 and left 5 again, gets us to -1, 3. And that gets us our new dilated square. And it was a square because all the sides were length 4. Now, what does that do? If the original sides were 4 and we scaled it up by 2, kind of means we took all of the sides times 2, and we can count the length of the side B prime to C prime. That's 8 units. So all of the side lengths doubled from the length of 4 to a length of 8. And we can see that in the picture. What generalization can I make for the area? Well, the original area is 4 by 4, which is 16. But now I doubled the length and doubled the width, so that means I quadrupled the area because I doubled and doubled. 2 times 2 is 4. So basically for that length, we take all the sides times the scale factor to get the length of the new sides. And for the area, it quadrupled because we take the area times 2 squared, or 4. Area on that new area on that last problem was 8 by 8, which is 64, which is the same as 16 times 4. Now, practice 12, is the quadrilateral ABCD a rectangle, a square, both, neither? Justify your response. Well, to be a rectangle, all the angles have to be 90 degrees. The opposite sides have to be parallel and congruent. To be a square, just one extra requirement, all the sides have to be congruent, not just parallel and congruent. So start with the slope from A to B is up 4, right 4, so that's a slope of 1. Slope of DC is up 4, right 4, which is also 1. Slope of AD is down 4, right 4, so that's -1. The slope of BC is also -1. So right now we know AB is congruent, or AB is parallel to CD, BC is parallel to AD, so we do have a parallelogram. Opposite sides are parallel. We also have AB is perpendicular to BC, because 1 times -1 is -1. If we multiply the two slopes and we get -1, they're perpendicular. We also have AB is perpendicular to AD. We have BC is perpendicular to CD, and we have CD is perpendicular to AD. All angles are right angles. Okay. Last thing, we got to check the length of the sides. Well, that's just using the Pythagorean theorem. 4 squared plus 4 squared square rooted happens to be square root of 32. If I simplify, that's 16 times 2. Square root of 16 is 4, so 4 root 2. And if we look at all of them, they're all 4 squared plus 4 squared square rooted. So all of these side lengths are the same. So opposite sides are parallel. All the angles are 90 degrees. Opposite sides are congruent, so it's definitely a rectangle. But it's also a square since all the sides are congruent. Now here's practice 1 and 2 I want you to try. Practice 3 is just like that last practice. You want to find length of the sides and whether they're parallel or perpendicular. You want to find the slopes. Practice 4, practice 5. You might have to add a little bit on your graph to be able to do this scale factor of 3. Practice 6. And that would be the last one.